So this video is about polymers, and as you know, there are different types of polymers, thermoplastic polymers and thermosetting polymers, and also elastomers are polymers. So in figure 415 of Ashby on page 63, you'll see that a picture of a thermoplastic polymer, and this particular one is polyethylene, one of the simplest of polymers, and you can see that there's a backbone of carbon that it's in kind of a chain, and in this top figure it's drawn to indicate that the covalent bonds in between the carbon-carbon atoms are they have a specific direction that they prefer to be in, and that's why you kind of have this structure here. And then if you're representing the molecule in a very simple way, you might draw it like this, where you just draw these carbons lined up with the hydrogens on the side, and the repeating unit is the CH2 unit here that's repeated a number of times. So when polymers have enough thermal energy, they'll actually rotate about these intramolecular bonds, so that if you were to apply a force to polymers, they can accommodate any kind of volumetric change you might be trying to impose on them by rotating about these bonds. And that's when they're above this temperature called the glass transition temperature. Below that, they act like a glass, and they're brittle, so that if you apply a force, they'll actually break. If you go to the next page, you'll see a number of other polymers pictured there in the simple kind of form. Again, here's the polyethylene, the one we just looked at, and then these are these other types of polymers I'm sure that you've heard of, polypropylene, polystyrene, and you can see that the difference between these molecules and polyethylene is that they have different pendant groups on the sides. So that's essentially the difference between polymers, is the different pendant groups that you get off the side, and pendant groups that tend to be larger, of course, tend to constrict the polymer rotation more, and they tend to be stiffer. Or if they are like chlorine, which is highly electronegative, they can actually cause kind of a stronger type of bonding inside the polymer structure, where you normally have just van der Waals bond between a molecule like this and then the adjacent molecule. But here you have van der Waals added in with a little bit of polarity when you have a molecule like chlorine on them. Now, if you also go to the next page, in figure 418, what you'll see is some, kind of schematic drawings of what you might expect to see in a polymer material. This is a non-crosslink polymer, and the green squiggly line represents the chain of the polymer all over the place. And you can see that if it's partly crystalline in a polymer, what that means is that there are areas within the polymer structure where the chain is sort of folded upon itself. Or if it's slightly cross-linked, these red dots indicate that there's a covalent bond linking two different polymer units together, and they add to the stiffness. Highly cross-linked, a lot of the red dots indicate a number of covalent bonds between the molecule, and molecules that are highly cross-linked are polymers like thermosets, which, if you know, are very rigid polymers because of this cross-linking.